In this chapter, we will learn how to conduct what statisticians call a test of significance, which is one of the most widespread tools in statistical inference. We will learn what the potent phrase statistically significant means and what it doesn't mean. Almost every day, we are bombarded with information that begs the question, have things changed? Has President Bush's approval rating changed since last month? Has teenage smoking decreased over the last 5 years? And even, did the Super Bowl ads result in increased sales? When North Carolina introduced a seatbelt law a few years ago, the rate of serious injury and death dropped from 4.7% to 3.8%. Now this is surely a lower rate, but not a lot lower. We know there is random variation and that the rate of serious injury and death will fluctuate from year to year. So is this decrease in the rate after the seatbelt law was passed due simply to chance? Statistics can help clarify ambiguous results such as this one. We can use something called a test of significance to measure the probability of getting a result purely by chance. Significant tests help us to determine whether a particular result is likely to be due to chance or whether some other factor is likely at work. Using significant tests, statisticians found that a drop in the serious accident rate as large as the one in North Carolina would happen less than 3 times in 100 if random variation was the only reason for the change. Well, that's pretty unlikely. So there is strong evidence that seatbelts save lives. The seatbelt example illustrates the reasoning behind all tests of significance. First, we will assume that nothing is going on. For me, the analogy to our legal system helps make the process clearer. When a person is convicted of a crime, the jury is instructed to assume the person is innocent and to keep holding on to this assumption while they listen to the evidence. When all the evidence is presented, the jury must then decide whether the evidence is strong enough to reject the assumption of innocence. Otherwise, they will fail to convict. Keep in mind that when juries fail to convict a person, this is very different from deciding the person is innocent. They simply cannot, based on the evidence, say without a reasonable doubt that the person is guilty as charged. So in statistics, we start out by assuming that nothing unusual is going on, analogous to assuming someone is innocent. Then we consider the data. That's our evidence. We find out how likely it is that our result could have occurred purely by chance. If the result is very unlikely or surprising, we have reason to believe that something is going on. We measure how likely or surprising a result is by something called a p-value, and we're going to learn how p-values are determined. So let's get specific about how to conduct a test of significance. Here's an example. In the 1960s, about 44% of the population had never smoked cigarettes. 35 years later, in 1995, data was collected on 881 adults, and it showed that in this sample, 52% of the adults had never smoked. The sample suggests that the percent who never smoke rose during that 35-year period. There certainly was a lot of research during that time that confirmed the tremendous health risks for smokers, and a lot of media attention was given to these health risks. So was the data collected in 1995 strong enough to conclude that the percent of non-smokers had in fact increased? Or could it be due just to chance fluctuations? In a test of significance, the assumption that nothing is going on is called the null hypothesis and is written H subscript 0. In this study, the null hypothesis says that there is no change in the percent of non-smokers, and that the percent in 1995 is the same as it was in the 1960s, namely 44%. It is important to recognize the general form of a null hypothesis. It says that a parameter is equal to some hypothesized value. In this case, it says that the true proportion of non-smokers in 1995 is still 44%. Nothing has changed since the 1960s. We also need to create an alternative hypothesis, which formally states that something is going on. It is called, logically enough, the alternative hypothesis, and is written H subscript A. So, in a test of significance, we compare data collected during an experiment to what we would expect to observe if there was no effect. This comparison gives us evidence either for or against the null hypothesis. Both the null and alternative hypothesis need to be expressed numerically. In this study, the null hypothesis states that the population proportion of non-smokers in 1995 is 44%, and the reasonable alternative is that it has increased and is now greater than 44%. Notice the null and alternative hypothesis are always stated in terms of the population parameter, not the sample parameter. Symbolically, we state P equals 0.44, not P hat equals 0.44. We do not test a hypothesis about P hat because we know what its value is. The value of P hat is 0.52. So how do we find the p-value, the probability that our result of 52% is simply due to chance and nothing has happened or nothing has changed? The proportion of non-smokers in 1995 is still at the 1960 level of 44%. We will go back to the sampling distribution of p hat. Our sample size of 881 is large, so we know that sample proportions will be normally distributed. We could calculate the z-score corresponding to a sample proportion of 0.52, the one observed in our study, and then decide if this was an unusual z-score. The familiar formula for how to create a z-score for a proportion is on the slide. So substituting 0.52 for p hat and 0.44 for p, we arrive at a z-score of 4.78. Now that is almost 5 standard deviations above the mean. It is extremely unusual. In fact, if we use the standard normal calculator, we could determine and announce that the chance of arriving at a z-score this large is almost 0. And that is exactly what we will do on the next slide. And this probability is called the p-value. So after calculating a z-score based on our data and the hypothesized p-value, we need to find the probability of getting a z-value at least this extreme. This probability is called the p-value. Small p-values give evidence against the null hypothesis, whereas large p-values fail to give evidence against the null hypothesis. Suppose we find a p-value of a 0.01. What this means is there's only a 1% chance that a result was due to random fluctuation. It is likely something else is at work. It is important to note that we never actually prove a null hypothesis is wrong. Small p-values simply indicate that it is very unlikely that it is correct. Conversely, we never prove that a null hypothesis is correct. Large p-values simply tell us that it could be correct. Remember the analogy to the legal system. The jury is never 100% certain someone is guilty. There's just a lot of evidence that they are. And that they are never 100% certain that someone is innocent. There is simply not enough evidence to convict or state that they are guilty. Since p-values can range from minuscule to very large, researchers are often faced with a dilemma. Does a particular p-value give enough evidence to reject a null hypothesis? With a p-value of 1 in 1,000, there is little doubt that the null hypothesis is incorrect. But what about 1 in 50 or 1 in 10? It is because researchers have so often come up against this kind of question that several fixed values of p-values are commonly used. The most widespread is 0.05. This means a result would be expected to occur only 5% of the time if the null hypothesis was correct. Statistically significant at the 5% level means that results produced a p-value of less than 0.05 and were therefore considered significant. It's important to pick a p-value appropriate to the situation. Suppose you are doing research on a new cancer therapy. Because your research could affect thousands of people, you might decide that a significance level of 0.05 is not good enough. Here you need to be more certain that the therapy works, so you decide to call your results significant only if they reach the 0.01 level. In this course, I will always give you guidance when it comes to choosing a significance level. We've done a lot, so let's take a moment to recap the steps involved in significance testing. First, decide and formally state both the null and alternative hypothesis. Many students fail to do this, and it definitely causes problems in later steps of this process. Next, calculate a z-score using the sample value of p-hat and the hypothesized value, the one in the null hypothesis, for p. Be careful not to use p-hat for p in the denominator. Use the online z-calculator to determine the p-value. And finally, state your conclusion in the context of the study. The next slide puts all the pieces of the analysis of the smoking data in one place. Notice in step 1, the null and alternative hypotheses are very explicit. Instead of just using the variable p, a little more detail is added. The hypothesis is about the non-smokers in 1995, not in the 1960s. Next, we calculate the z-score. The alternative hypothesis said that, if anything, the non-smoking rate in 1995 should be higher than in the 1960s. So we are looking for the area above a z of 4.78. This area is so small that the shading does not even appear on the graph of the online calculator, but the p-value is given in the bottom in blue. Since the p-value is incredibly small, it is very unlikely that this result could be attributed to chance. So we decide to reject the null hypothesis and go with the alternative. We conclude that the proportion of adults who never smoked in 1995 is higher than it was in the 1960s. It is very important that when you decide to reject the null hypothesis, you quote the p-value. This lets the reader know how likely it is you reached the wrong decision in rejecting the null hypothesis. Sure, it is possible that nothing has changed since the 1960s, but the likelihood that this is the case is considerably less than 1%. As a final detail, we could use the procedures from Chapter 7 to establish a 95% confidence interval for the percent of adult non-smokers in 1995. What is interesting is that the interval goes from roughly a 49% to a 55%. Since in the 60s only 44% of adults were non-smokers, and this interval contains values that are strictly larger than 44%, we again have evidence that the percent of non-smokers was higher in 1995 than in the 60s. The nice thing about the confidence interval is that it gives us an estimate of what the 1995% of non-smokers actually was. In general, every time you reject a null hypothesis, it's a good idea to follow it up with a confidence interval estimate. Then you have a complete picture of the situation.